Okay, so in this video, I'd like to do a basic introduction to crystal structure. So to start with, you know when we heat a metal up, or you may know you heat a metal up and cool it down, we see little crystals form. Sometimes we sketch the microstructure in a little circle, and we might say you've got some liquid, and then as you cool it down and it first starts to solidify, you get little crystals form. And this is something that we cover in more detail in phase equilibrium. But the concept you might be familiar with. You may have seen this in, say, looking at a jar of honey or something like that that sits on the shelf for a number of weeks or months. And you see little crystals of sugar form in it. And what actually happens initially is some little sucrose molecules slow down, often on a rough feature, a little scratch on the inside of the container, or if you put a string into a container of honey, the rough little features on the string will actually serve as low energy nucleation sites for sugar crystals to start to form. And so what happens is some little molecules of sugar will slow down and deposit on the string in that example, or in this case with a metal solidifying. A few atoms of a metal will come together and they'll form a metallic bond, and they'll start to form a crystal. And so more and more crystals will start to, or atoms rather, will start to deposit on top of that. So if I sketch, just in sort of a cartoon sketch here, a little call out of that crystal, what that would look like is a little collection of atoms that's arranging themselves. And I'm doing a very generalized example here. They're starting to come together and achieve a lower energy by forming a metallic bond, and they arrange in a very regular repeating pattern. And I'm trying to illustrate that here just as this simple orthogonal arrangement of atoms. But that particular repeating arrangement, that regular repeating arrangement, is what we refer to as a crystal. And often in material science, the word that we use instead of crystal is grain, but really they're synonymous. Okay? So we know that atoms in a solid may form in a regular repeating arrangement as crystals. They don't have to. Glasses are amorphous, and we'll cover that in another video. But if they do form a crystal, there's a regular repeating arrangement to it. And if we'd like to describe that to help us appreciate the properties of a crystal, or of a solid, for example, we'd like a way to describe the crystal without having to describe a million atoms and all their positions. So could we sort of take that little arrangement there and break it down into a small chunk? And sometimes it's useful to think about a two-dimensional analogy. So a two-dimensional analogy would be, say, a wall that you're covering with tiles. In fact, this classroom has these bricks that are actually, in this case, I think they're structural part of the wall, but there's a pattern to them. You can see they have this rectangular shape, and if I wanted to describe the wall, I could sketch the entire wall for you, but I could also break it down into the individual brick. And if I account for half of the grout line between the bricks, I could actually describe essentially the wall by describing a smaller number of bricks and just defining their dimensions, perhaps height and width. Maybe I'll call it A and B just for these purposes. And we could call that little unit, well, we could call it a building block. And in fact, I don't mean specifically because this is a brick that I'm calling a building block. I just mean some unit that we're repeating to form the larger structure. In this case, we're limited to just two-dimensional in this example. So we could cover the entire area with these little rectangles. So what we could look at then is, again, in the two-dimensional example, what would be some possible repeating units other than a rectangle that we could use to completely cover an area? So we'd say it must completely cover the area. You know, with no voids. Well, we could certainly use a square. You could translate a square up and down and so on, right? And completely cover the area, and 100% of the area would be covered. Right? So we'd say, yes, that's possible. What about, you know, if I took, for example, a circle? Well, a circle, even if I really tried to squeeze them in to cover the area as carefully as I could, there would always be some void space between the circles. You know, and I didn't draw those circles very well. But circles do not have translational symmetry. You can't slide a circle adjacent to itself and completely cover this, this area. So we'd say no translational symmetry. Okay. What other shapes could we have? Well, what about you know, a parallelepiped, or like this, and these sides are all meant to be parallel. Well, certainly yes, you could translate that over as well and completely cover the area. So that would work to cover an area. What about a triangle? Well, a triangle, if I translate it without any rotation, the triangle would not cover the entire area. Again, there would still be this missing space, this, if you will, void that's not filled. So a triangle on its own doesn't work. So you start to get the idea that there's certain units that we could use to cover two-dimensional space. What about in the three-dimensional world? Well, in the three-dimensional world, of course, sort of the extension of the square would be the cube, and that could be translated to fill three-dimensional space. I could draw another cube to the right of this one, and so on, and up and down and front and back, and fill a volume completely with cubes. There's other there's other solids that we can use as well, and we'll explore some of these later. Today we're really going to focus on the cube because actually there's a lot of materials, many materials have cubic symmetry. And that's convenient because the cube is relatively easy for us to understand as humans. We're comfortable with an orthogonal axis system. You know, x, y, and z, we're fairly comfortable with already. So that one works nice. So it's kind of a convenient result of nature that many materials have cubic symmetry. So if we then say our building block is going to be a cube, there's a few things that we should describe or be able to describe about the building block here. So first of all, these repeating units or building blocks, we have another name for them. So instead of calling them building blocks, we call them unit cells. Okay, so what I've sketched over here then is a cubic unit cell. And we should be able to describe the dimensions of the cube. So we would need the cube edge length. And of course, it's a cube, so each of the dimensions, the linear dimensions, is equivalent. And commonly, we just refer to them with the lowercase letter a. Over here, I went ahead and I described another dimension, b, for this rectangular two-dimensional shape. And similarly, in some volumes, some three-dimensional unit cells will have the height, for example, if this was tetragonal, it was like a cube that's elongated a little bit, we would have a height that was different than the base dimension. And so we'd have a value of a and b that we'd have to define. And what we call those are the lattice parameters. The lattice parameters. So we've got only one lattice parameter in the case of a cube. If it was a rectangle, we would have, you can see, two lattice parameters. And I should also, just for a moment, expand on what this word lattice means, in case, and it's if English is perhaps not your first language, you may not have come across that. But lattice, the word lattice essentially describes a repeating framework. For example, you could have a lattice in your garden, and you could grow a clematis or something on it, some climbing vine. So in our case here, we've got a lattice. You could have a two-dimensional lattice. It would be a two-dimensional positioning of points. So we could say, let's put an atom at each of these intersections. And then what if we took that into 3 dimensions? Well, then we would have the basis for our unit cell over here. So our unit cell is essentially a small little piece of the lattice. That is, if we repeat the unit cell front to back, up, down, left, right, we'll build this lattice. And there's positions, various different positions in the unit cell that we could put atoms. So I haven't told you yet where they're going to go. That'll be the focus of another video. But right now, we've just described the unit cell, the concept of a lattice, the lattice parameters. And a little bit later, we'll also look at cases where these angles are not orthogonal. In this case, for a cube, of course, they're 90 degrees, but later on you'll see some cases, hexagonal close back, for example, where one of those angles is 120 degrees. So I think that's a good place to stop for this initial video. Thank you.